Hello and welcome to the video lecture for Chapter 6, covering the first part of Chapter 6. In this lecture, I'm going to talk about work and power. That gets us up to about half of the slides. There's some 48 slides in this lecture. All right, and in this chapter, which is from the Physics of Everyday Phenomenon, 10th edition, Conceptual Introduction to Physics, by Thomas Griffith and Juliet Brosing. Okay. So we have done videos in the past if you've been watching my videos for this textbook. So we're just going to carry on, all right? And the last thing that we were talking about was the study of gravity, so a reveal of a fundamental force, and a study of circular motion, okay? Well, we're not talking about that anymore. We're doing something totally different. We're talking about energy, okay? Now, energy is interesting because energy is best understood in processes that repeat themselves, because then we can clearly see a conservation of energy, like the swing of a pendulum in a grandfather clock or a swaying chandelier. What we see is a conservation of energy. We see a exchange of, as we know today in our modern understanding of physics, one form of energy changing to another. Gravitational potential energy, a term that we'll be talking about in this chapter, changing to kinetic energy, which is the energy of motion. That word kinetic means moving, so kinetic energy is the energy of motion. They both have particular forms. These are consistent with derivations that come from basic Newtonian mechanics, but they aren't basic Newtonian mechanics in the sense that when Newton was expressing the laws of physics and calculus and coming up with this foundational set of rules for motion, energy was not part of the picture, okay? Certainly not the way that we know energy today, the way we'll define force, or rather work, as force times distance, or kinetic energy being 1/2 mv squared. Don't worry, I'm going to tell that to you again. You'll see that formula. So all those expressions for energy, those come later. In fact, they come in the 19th century. So it wasn't until the 1800s that there was an actual kind of prevalence of thinking about conservation of energy, not as new physics, because it doesn't add anything fundamental to Newton's laws of motion and Newton's law of universal gravitation, sort of these grounding laws that we've seen. All it does is it gives us a new tool, which is valuable, right? Not new physics, just a new way of tracking something, identifying this concept of energy, expressing it in as many forms, right? And we'll just be talking about some of them today. In fact, the types of energy that we'll talk about in this chapter, in Chapter 6, are all mechanical energies. And so we will talk about gravitational potential, elastic potential, and kinetic energy, the one I mentioned, the energy of motion. So those three are considered the big three mechanical energies. Now, it's kind of interesting because elastic energy comes from the fact that solids, if you stretch them, they want to return to their original position. Really, what's causing that is molecular forces. The molecular forces are, in fact, electromagnetic, largely electrostatic, but electromagnetic. And, well, that's definitely not a mechanical force. But in the macroscopic world, we don't really think about the fact that it's an electric phenomenon happening at the atomic level that makes materials stretchy. But we do certainly think about how it's gravity that makes things fall. It's gravity that is driving the swinging pendulum, okay? It's, as also shown at the beginning of the chapter, right, a different swinging pendulum. This one looks actually like a plumb bob, which is a particular kind of big metal pointy attachment. It is really a pendulum hanging on some small string, and traditionally a plumb bob is used, as shown in this figure, to point straight down so you know the exact direction of gravity, right? Because maybe your tabletops and your floors aren't exactly flat, but you know this string, with a heavy weight at the end, is pointing straight down, and the heavy weight has a little fine tip point, so you have some precision on it. Okay, so kind of a classical device, used for hundreds of years, right, as a physics, necessary tool. Although these tools are getting phased out, right? Now we can just pull out our phone and know the exact direction of down or something, right? Because we have such good sensors built in, micro sensors built into so many electronics, which are pretty darn accurate. But all that aside, we're talking about energy, and I was saying that clearly gravitational energy and gravitational potential energy is mechanical. Right? Because mechanical is everything that's not nuclear, that's not electromagnetic, right? It's mechanical physics. Okay? In a sense, mechanical physics is gravitational physics, but it's also the physics of the everyday. And so elastic potential energy, elastic phenomena in general, get lumped in with mechanical physics, and that's no exception here. Now, things just moving, right? The ideas of velocity, acceleration, how forces create motion, Newton's laws, those are also all mechanical. Newton's 3 laws of motion are mechanical laws. Okay, so you see that motion, also gravity, right? That's what's considered mechanical. And the definition is a little hard to pin down, right? Is it everyday or is it actually gravitational? But it gets thrown around a lot. What you should remember is when we talk about mechanical physics or mechanics, sometimes we call the whole field of study of mechanical physics, we just call it mechanics. All right, not to be mistaken with a person that's a mechanic, right? This is the study of mechanics, the subject. Well, that is in contrast to what it's not, right? As I said, if you're talking about mechanics, you're not talking about electricity. You're not talking about heat flow, so no thermodynamics. You're not talking about quantum mechanics or anything on the microscopic scale. You're not talking about relativity, Einstein's famous laws. So it's everything that's not that. Okay, so in a sense, is mechanical physics just classical physics? Is it just the very first things we had? Yes, in a sense, right? Because as we get into another subfield I even mentioned in my summary there was fluid dynamics. That's another subfield of physics that would not be. In that sense, that one is sometimes called mechanical, right? Because fluids, just being driven by motion, right? They are a mechanical system, aren't they? But they have their own unique rules because we're zooming out. We're not looking at every particle of that fluid behaving independently. We look at the fluid behaving together collectively, and it doesn't behave like a pendulum bob, right? It has very different things. It sloshes around. It's got this whole idea about viscosity and so on, right? Fluids behave uniquely relative to solids, right? And everything in between, viscoelastic solids, So the subdivisions of physics are so many, but again, mechanics are the very beginning things. Is conservation of energy, if it's mechanical energy, firmly within the that subdivision of mechanical physics? Yeah, it is. Okay, so that's definitely where we're at, and we'll continue to be there when we talk about momentum in the next chapter. When we talk about the momentum, okay, in chapter 7, right? That's also going to be mechanical physics. All right. So the force does work. I like that word. Okay, to move the ball. This increases the ball's energy, affecting its motion. Okay, so it doesn't increase just any energy. It in fact increases its kinetic energy because it already had energy. So a well-known concept in physics that sort of branches out from people saying I don't know anything about physics. Well, one thing that is kind of widely known, one of those little tidbits that makes its way out into general knowledge, is that energy cannot be created or destroyed. Or maybe it's phrased, energy can neither be created nor destroyed. Right? It's just there. Right? It can change from one form to another. So to say that the ball's energy increases, well, no, just one form of its energy increases, okay? And that would be its energy of motion, all right? But it already had energy. In order to do that, it had potential energy. Why? Because it was capable of falling. Now, the thing about pendulums, fascinating thing, is they can't fall straight down. It's not like dropping something and letting gravity do, the maximum amount of work. You're restricting it to this particular path. Okay, which ends up being really fascinating in terms of the form of acceleration, because you do have this steady sinusoidal acceleration, and that idea that it ties in with the mathematics of trigonometry, the mathematics of circles. No surprise, it is after all a segment of a circle. It makes it actually really incredible, right? And then the way our understanding of circular motion, or in this case partial circular motion, and an oscillation and sine waves and cosine waves, helped scientists, continues to students, but originally helped scientists understand that type of phenomenon in electricity and building circuits that oscillate. And so it's kind of this idea that that if we have a foundational understanding as humans, we can extend that idea to something else. So one of the first things we'll talk about before we define that word work, which has a particular definition in physics, is not the way we use work in everyday language. But before we do that, let's define a simple machine. So a simple machine simply multiplies force, okay? So a machine, okay, by definition is a force multiplier. Now, you may be like, well, some machines don't just add force. Well, sure, yeah, we use machine differently in everyday language. But in a mechanical physics definition, a machine is just anything that multiplies force, all right? How do you multiply force? One way with fluids, and we have a chapter on fluids later on, is with something called Pascal's principle. That's how you build a hydraulic system. And hydraulic systems are all built on conservation of pressure, which itself is really conservation of energy, but within the fluid. And then it ends up being that you can have different surface areas on the input and the output, and then that allows greater force on the output, because you usually want more force on the output. You want to put in the small force and get a big force in return. But you have to give something up in the case of a hydraulic system, and you always have to give up distance. So sure, you can get a big force multiplier. You can put in a little bit of force, like literally like a human pushing on like one end of a hydraulic system. But when they push, they're going to push a very long distance, and they're just going to get, say, the car on the hydraulic lift to just move up a little bit. Okay. And we deal with that in some terms of ratchets or something. And I bring this all up because hopefully that kind of gets our gears turning and visualize something. And honestly, a simpler version of what I'm talking about is simply a lever, because a lever is exactly that idea. You put in a smaller force and you get a bigger force in return. You do that by putting the pivot closer to the thing you want to lift, right? Or just wherever you want the bigger force to be. Because whatever has the shorter moment arm has the larger force. Why? Because torque in equals torque out. So whatever torque you put into the system, torque, if you remember from our rotational chapter, is force multiplied by the lever arm length. Okay, so that it's an equivalent of rotation. Oh, actually, we haven't talked about rotation yet. I was thinking about as I was preparing that lecture, but I have not recorded the video for rotation yet. We actually will cover rotation later on. But when we talk about torque, when we talk about rotation, we'll talk about how it's the equivalent of force, torque is, but in rotation. All right. And so we're actually seeing here is a conservation of torque. We're seeing that whatever torque you put in, you get out. But in terms of a machine, we apply a small force. You can see over here it's a shorter force vector over a larger distance. Okay. And then that's going to equal a bigger force over a shorter distance. Right. Now, sure, you gave up distance, but in return, you got the ability to lift something that you otherwise would not have been able to lift, because you simply, maybe as a human pushing on the other end of this lever, just weren't strong enough, okay? You multiplied your force. The lever is a simple machine. It's a force multiplier. Now, what's cool about it is it conserves the very quantity that we're highlighting in this chapter, energy. And it conserves it in a form called work. Because as we're just about to see, right, we're going to be talking about work and power, right, in this video, in fact, right? That is on all the chapter, but it's the first half, that this product of force measured in newtons times the distance that force is applied over, okay, especially in this case where they're all parallel to each other, so it's literally just multiplication. So force times distance is work. So whatever this product is, small force times big distance, right? So maybe this is 1 Newton times 2 meters, right? So product of 2 Newton meters. Those are the units of work, okay? Well, that's going to be the same over here, right? So I said this was 1 Newton and this was 2 meters. So let's say this is half a meter and this is 4 newtons. Well, 4 times 0.5 is 2. So we still have 2 Newton meters on the output, 2 Newton meters on the input. We have conservation of energy in the form of work. Work is in fact energy. Energy is work, all right? I'll remind you of that. It's easy to forget. But we have this very idea that energy cannot be created or destroyed. Whatever goes in, comes out, okay? So another way to get a force multiplier is a pulley. Pulleys are kind of cool. They bring us back to the kind of the free body diagrams, summing forces, thinking about net force, thinking about Newton's law, especially Newton's second law, F equals ma, particularly F net equals ma. So it brings us back to all those ideas because we see a couple of parts of this figure over here, a pulley with 2 tensions acting on it, and then a weight which is being acted on by the box. Let's think force pairs real fast. So the hanging box here experiences a weight. The other half of that force pair is the box pulling up on the earth, right? Which we're not going to notice, right? Or at least the earth's not going to notice, right? No one will for that matter, right? So then you think about another force pair. Then the force that is going to pass up through kind of the tension of these cables up into wherever this metal joint is. That's going to be a force that's applied to the pulley, right? So the box pulls on the pulley pulls back on the box, okay? Especially because the pulley's motionless, so our F net equals 0, so then we know the 2 forces are exactly equal to each other. If the system's not motionless, then they're not exactly equal to each other. The difference between them is an ma, okay? But and then we'll say everything is static or motionless here. So the box pulls on the pulley, but now here's where things get interesting. The pulley has 2 strings supporting it, okay? So whatever is the weight of the box, well, that's equal to 2t, see, right? 2t equals w. So that means that T equals 1/2 of W. Now one of the T's is supported by the ceiling. That tension pulls on the ceiling pulls back on the tension, and that force pair is, remains because the ceiling's not going anywhere, okay? So that means that if you carry this tension over to another pulley, the purpose of this pulley just to redirect the rope back down to where it's convenient to grab, we're into that, because you could have someone standing up on a ledge up here, right, and still have the hook. The point is that now wherever the person's pulling, whether they need another redirecting pulley or not, they only have to deal with half of the weight, okay? So they have done a force multiplier, right, in the sense that they put in a force and they're able to get twice the force out, okay? So it's interesting because it's not a lever, right? But it's the same principles where we're conserving something, right? But we're conserving it by having more than two bodies here. It's not just the pivot and then pushing on one end of the rod and the other end of the rod. We have the ceiling, we have gravity, and we have the person. So we have three and more, potentially more if you have redirecting pulleys. Okay? So you have an advantage of two. So finally, the formal definition, here it is in writing. Okay? So work, we represent it by the letter W uppercase. All right? But in word form, it would be work equals force times distance. Okay? So this is a new physical unit. All right? We don't introduce new physical units lightly in physics. It's a big deal. We only do it when we absolutely have to. Right? So that's the thing, right? Because physics is all about distilling things down to as few core principles as possible, which is why it can seem tricky up front. But honestly, it's a straightforward endeavor. What are the fewest number of building blocks we can have? Well, work's going to be one of them, right? So far we've got velocity, acceleration, force. Okay, basically that's it, right? And then like displacement and time, right? Well, this is a new one. Now, I said it's not necessary physics, right? It doesn't introduce anything new. You could actually do all of physics without the concept of work and energy. But it's incredibly helpful. There are so many situations where it is just a tool that has helped people reason through physical dilemmas, reason through kind of understanding our universe. All right. So yes, it's not strictly necessary, but since it's conserved, it falls into that category of being incredibly helpful and incredibly formational for physics. Okay. So here it is, our new unit, work. All right. So work, by definition, in formula form, in variable form, W equals F times D. F for force, D times distance, all right? Now, F is measured in newtons because it's a force, okay? D is a distance or displacement measured in meters. Therefore, we express the units of work often as actually Newton meters. We just call them Newton meters. But we don't have to because there's another variable, another derived unit called the joule, right? Named after a scientist. A scientist actually studied heat engines, but heat engines were very important to this understanding of energy. In that case, they're really seeing energy, conserved through what you think of as an engine, maybe a machine, which is more like a combustion engine or a steam engine or something, right? But historically, this comes later. Regardless, the name comes from that, named after joule, right? And that's pronounced joule, Joule, right? The letter for the unit, and we put unit letters in parentheses, unlike variables that we leave out of parentheses, and that's just the J, okay? So that's the unit of the joule, not a base unit, but a derived unit from base units, because the joule is precisely the Newton meter, and the Newton is precisely the kilogram meter per second squared, because it's just the mass times acceleration. Mass kilograms, acceleration meter per second squared, okay? That means the joule is the kilogram meter squared, because you pick up an extra meter, per second squared, okay? So let's look at some cases of pulling on things, and I'll remind you of those units when I'll do a analytical or numerical example at the end, all right? So again, the sections we're going to talk about, I want to quickly show you that here in the book before we go through a series of questions, is we have the simple machine, right? Work and power. So that's you can see there's some figures like this one, considering pulling on something. And I'll highlight the way you're pulling on it. Obviously, person's kind of pulling up on it a little bit. There'll be a definition of power, all right? And then we'll leave off on kinetic energy. So 6.2 will be in another video, okay? So here's the thing about doing work, because you can often exert a force on something and not do work, right? So if I just push on the wall, right? So over here, let's take a look at my poster, right? So if I go and I just push on the poster, am I doing any work on the wall? No. Now I'm providing a force to the wall, but I'm still not doing any work, right? It's like a useless force in a sense. because you think of work as like what you want to get out of a force. But I'm not doing any because the wall didn't move. So one thing is that it's definitely possible to apply a force, a non-zero net force, onto something and have work be zero. One big reason is that one big way that happens is when the object that the force is being applied to, okay, that's your free body, right? A box, often we consider it, right? Maybe a particle, right? In this case, a wall, right? Or a person or a car or anything. So that object, if it doesn't move, no work, end of story. Because remember, the definition was force times displacement, right? It's the product of the two, one multiplied by the other. Well, if D equals 0, then W equals 0. Plain and simple, okay? Right? So no work done. But there's another way to do no work, and that's to apply a force that's perpendicular to the displacement. So interestingly, we actually saw that force. There's a famous force that always does zero work. That's the centripetal force. Think about it. The centripetal force points to the center of the circle. Which way is an object moving? What's the instantaneous velocity of an object that's moving in a circular path? Tangential to the circle. The angle between those is always 90 degrees. That means that the centripetal force, like gravity, right, because there's many forces can play the role of a centripetal force, does no work, none, okay? But we'll see that makes perfect sense in the next video when we talk about kinetic energy, because it turns out if non-zero work is done, in other words, if a force does work, then kinetic energy changes. Kinetic energy changing means that speed changes. Okay, so any change in kinetic energy means a change in speed. Okay, as long as your mass stays constant, which we'll assume. So, oh well, that definitely doesn't work for circular motion, because circular motion is all about maintaining a constant speed. Aha, right? So that kind of makes sense that the centripetal force does no work. No matter how strange that seems, right? Because after all, satellites are in free fall. Their whole path is dictated by that force, but yet the force does no work because it doesn't change the speed of the satellite. Okay? So only forces parallel to the motion do work. Okay? So what if a force is partially parallel and partially, perpendicular, right? Not the case where it's, perfectly parallel or the extreme centripetal case, perfectly perpendicular. Well, then you only look at the part that's parallel. So in this case, this person who's pulling up on the box as well as to the right, well, they have two components, which you could find with the Pythagorean theorem. You could just find from the fact that you've got a squared plus b squared equals c squared, right? This is what's called a 3, 4, 5 triangle, because 3 squared, right, plus 4 squared equals 5 squared. In other words, 9 plus 16 equals 25. Okay, so it's pretty cool. Right triangle, right? Famous one. So sum of squares being a square sort of thing. So regardless, right, no matter how pretty this triangle is, mathematically speaking, it's just a triangle. It's a right triangle, right, 90 degrees. The reason it's a right triangle is because we split the applied force, right, which could be at any angle, right? But we split that applied force into two components. The one that's capable of doing work, which is the parallel component, and we split it into the perpendicular component, the part that is incapable of doing work, that'll do zero work, okay? Now, it just so happens that in this picture, and to keep it nice and simple, those components are exactly match up with horizontal and vertical. That's fine, that may not be always the case, but it would be in this class, okay? Now, that's great though, because we can clearly see that it is only this component, the parallel and also horizontal component, that is capable of doing work, right? So we say then that the 30 Newton part of the diagonal force, that's the 50 Newton force, does work. The 40 Newton part does not. Okay? All right, so we've got part of the force capable of doing work. All right, which part? The parallel part. All right, now I got another definition for you. Power. Okay? So we have a simple definition for work, just force times distance. Okay? And that gives you energy. We'll talk more about why that makes sense, but that's because you can start to do things with that work, right? Well, another thing is how quick did you do the work, right? Because if you did the work over a certain amount of time, and you measure that time, now you have a measurement of what we call power. So the strict definition of power is just work per time, okay? So it's work divided by time. It's how much work you did in a certain amount of time, which makes a lot of sense, right? It's actually saying that out loud that should be the definition of power, okay? Now, in the mechanical sense, right, sometimes it's going to be like really rudimentary, like literally a force, like pulling on a pulley, a certain distance, right? And then that's our direct measurement of work, and it took 1 second for that thing to happen, right? Some actual physically pulling something. And so then we'll say, oh, well then that's how much wattage went in, okay? Because the watt is the unit of power, which is just the joule per second, right? So again, these are units, the unit joule over the unit second. These are variables, the variable work over the, for work, W, over the variable T for time. I highlight that because as we go and introduce more and more equations in physics, it can be tricky to get, to keep track of all these letters, right? And you want to make sure that as you're keeping track of these key formulas in physics, luckily there's not that many, you need to know what are variables and what are units, okay? And this is a clear case where we want to make sure that we acknowledge that, this is an equation of variables, okay? And each of those variables have their own units. P has units of watts and W, okay, power. W for work has units of joules, represented by J. T for time has units of seconds represented by S. Did you notice, right, that the letter W comes up twice? W for for power, right? So P has W, but W has J, right? So keep track of that, okay? All right, so the few questions before I do a numerical one. So some concept questions. So I'm, sort of pseudo-numerical, but then we'll do a full numerical one to wrap things up. So a string is used to pull a wooden block across the floor without accelerating the block, okay? We'll talk about why that's important when we talk about what's called the work energy theorem, this idea that if you do a non-zero amount of net work, then you get a change in velocity. What's another way to quantify a change in velocity? Acceleration, okay? So the string makes an angle to the horizontal, so it's another diagonal force, only some of it's going to be doing work. So does the force applied via the string do work on the block? What do you think? Right, so we're applying this force, right? We're told that the block does move across the floor, but it just doesn't accelerate. Is work done? What do you think? Lock in your answer. What do you think? Okay, all right. So yes, right, only part of the force does work, right? But it does. We do it because there is a displacement in the distance parallel to the horizontal component of the force, okay? So there is work done because there is at least some displacement in the direction of some force, okay? Since that criteria is met, there is definitely work done. Now, interestingly, the fact that it doesn't accelerate is something we haven't talked about yet, but that means there must be at least one other force, because the only thing that could prevent this block from accelerating is, well, most likely a friction force. So that means that friction will also be doing work. Friction will be doing exactly as much work as the horizontal or parallel component of the diagonal force. How do we know? Because those two works summing up to zero, yes, we sum works just like we sum forces, although they're scalars, not vectors, which makes them honestly easier to sum. They can either be negative or positive. We don't care. They don't point in any direction. Okay? I'll repeat that in a second. But the point is we sum up those two different values of work, the work done by friction and the work done by the diagonal force, okay? Right? So that sum, we know it's zero. How do we know it's zero? Because if it wasn't, there would be acceleration. But more on that later. I just want to kind of lay that out now. By the way, I repeat it, that work being a scalar is key, right? Because notice we keep talking about force creating work, but when we define work back here, did we ever define it with a arrow anywhere? No. The only arrows in these figures are the arrows of force, and then we kind of show displacement as like a two-pointed arrow. It's more of a habit than a physical reality. Displacement is also a vector, right? It also should point in one direction. It's either going to point parallel to the force or what we call anti-parallel, So anti-parallel would be just the opposite way. So in both cases, there's non-zero work, because as long as they point along the same line, you get non-zero work. But if the displacement was exactly the opposite way of the force, so those are forces like friction, which are trying to impede the displacement, right? Trying to bring things back to rest. That's what friction does, right? Or air resistance, right? Otherwise known as drag. So when you have the force pointing one way and you've got the displacement pointing the other, right? A retarding force, friction. Well, that is what's called negative work, because it takes kinetic energy out of the system, okay? But it's still non-zero work because it's still along the same axis. But that's work being a scalar, not a vector, okay? It can either be negative or positive, yes, but that does not make it a vector. Scalars can be negative or positive. They're still numbers, because the key difference between a scalar and a vector was that vectors have direction and magnitude. Scalars are just magnitude. What scalars have we seen? Time and mass, okay? Well, and speed, right? Time, mass, and speed all could only be positive, but just kind of by definition, right? That wasn't something like sacred to scalars in general. That was just those particular scalars. So now we have a scalar work that can be negative, okay? Just something to take account of. Still a scalar though. All right, another question. So if there is a frictional force opposing the motion of the block, does the frictional force do work on the block? Okay, does it? So think about it, right? The frictional force, that's this arrow now, shown there. I said that it is going to, still be kind of a version of parallel. And I did say that it does, right? So what's the answer? Yeah, absolutely. The frictional force is what is called anti-parallel, okay? So it does negative work on the block, okay? So it just picks up a negative. Anything that's past 90 degrees, right, has at least a parallel component, and then will do negative work. So does the normal force of the floor pushing upward on the block do any work? Because if this is on some flat table and the table's at rest, then there's going to be a force pair of equal and opposite magnitude, right? In fact, and also no acceleration in the vertical direction. So the weight, or rather the apparent weight, the block pushing on the table will then cause the table to push back, right? I'm hesitant to say weight because the force pair with the weight is actually pulling back on the earth. Here we care about the force pair between the table and the block. But the point is the forces on the block are what we really care about, and one of those is the normal force. Okay, normal force is by definition a force supplied by a solid surface that is always perpendicular to that surface. Okay, so does it do work? What do you think? Nope, because it has no parallel component. It's completely perpendicular, and it does no work at all. So we've got the friction force doing negative work, we've got the diagonal pulling force doing positive work, and we've got the normal force doing zero work. Right, let's look at some values. So a force of 50 newtons is used to drag a crate 4 meters across a floor. The force is directed at an angle upward from the crate as shown. What is the work done by the horizontal component of the force? Okay, so you've got your displacement of 4 meters, okay? You've got your force, your total force of 50 newtons, okay? So how are you going to calculate the work? Remember, work is force times distance, but it's not just any force times distance, it's the parallel force times distance. Okay, lock in your answers. Okay, so it's going to be the 40 times 40 or the 160, because the full 50 newtons is not what you use to calculate work. How do we know? We know because only some of this diagonal force is actually doing work. Remember, the 30 newtons does no work. So in this case, the 40 newtons is parallel to the 4 meter displacement and does work. So it's the product of the 40 newtons and the 4 meters, which is the 160 joules. Okay, so option B. All right, what is the work done by the vertical component of the force? I bet you know this one. All right, you, okay, yes, 0, okay, absolutely. Because there's no displacement in the vertical direction. Cool, all right. So what is the total work done by the 50 newton force, right? Because we got the 50 newton force is diagonal, the vertical component does 0, the horizontal or parallel component does 160. So what's the total amount of work done by the 50 newton force? Just the 160. 0 plus 160 is 160. See? So you really only have to care about the parallel component. You can completely ignore the perpendicular component, because doing 0 work really means doing 0 work. It does not affect the total. It does not affect the system. Okay? So we'll talk about kinetic energy next time. All right? This is kind of a cool simulation where you can set different masses of pulling a cart uphill and look at the work. So let's say we want to take a 3 kilogram mass, all right, and we're going to pull it up a 40-degree angle, all right, and so there's our angle, there is our mass, there, and the height. So the height is not the hypotenuse here; it's just the vertical component. So we'll run the trial, right, and this will tell us, the force that it takes. Okay, so we had to pull with an 18.9 Newton force, okay, to pull this thing uphill, all right? So that means, like, you think about how much effective work did you do, to pull it uphill, right? Because you pulled, in this case, you're pulling parallel, right? But your displacement isn't parallel to the force of gravity that you're working against, okay? So then, if we were to change the angle, right, to 90 degrees, do you think you'll have to pull more or less to pull it to the same height? Okay, let's see. All right. You have to pull with a greater force, okay? Because now you're opposing the full work done by gravity rather than just some of it, okay? Well, let's look at the least steep angle we can choose. We've kept the mass at 3 the whole time. So what if you want to, raise it to a height of 1 meters, and you pull at a relatively gentle angle of 30 degrees, look, now you need 14.7. It doesn't go down dramatically, but it's gone down. Because again, you're doing work, the external work of your hand is opposing the work done by gravity if you just want to move something at constant velocity and we're ignoring the initial and final acceleration. So you're kind of doing the minimum amount of work. And the steeper the angle, the more you have to actually work against gravity. The less steep the angle, you still get the overall change in height, right? So you're still kind of like getting the same return in a sense, right? But you're letting the ground do some of the work against gravity. Because now the normal force, right, isn't doing work, but it means that you don't have to do all the work, because the normal force is at least supporting the object. It's not pushing it uphill, right? So because it's always going to be perpendicular to the displacement, but it's absorbing some of that force. Okay, it's just pushing back from some of that force, preventing it from accelerating down. Okay, you don't have any of that prevention when it's perfectly vertical. So it's that same sort of return, right, that we saw with the simple machine. If you wanted the force return, then you had to push a longer distance with a smaller force, and what you got in exchange was a bigger force but a shorter distance. Well, here, if you want to apply a smaller force, then you have to do it at a less steep angle, right? So you can still get the same change in height, but you're going to have to pull it much longer, because look, the hypotenuse just gets longer and longer. All right, interesting. Okay, so with that simulation in mind, let's go ahead and do a single numerical example to wrap things up. Okay, so this is just going to be a work example. Okay, so we will have a block of mass 12 kilograms, okay? And we're going to apply a force. So use a pink over here, all right? So apply a diagonal force, all right, like so. And then some of that force is going to be parallel, okay? So we'll call this F parallel. That little symbol, the two side-by-side bars, literally parallel lines, means that this is the parallel component, just like I might write X for X component. And then this one, I will give you a value on it. I'm not going to give you the main value because I didn't care about the angles here. But I'm just going to say then that this force over here is going to be 13 newtons, okay? So then the actual wording of the example, so is if the force shown is applied to move the box, right, of mass m a distance, so mass m, a distance of 6 meters, then how much work does the force do? Okay, so how much force is done, rather how much work is done by the force. Okay, so got the calculation? Make sure you can work it out. All right, how much work is done by the force? Okay. All right. So did you need m in your calculations here? No, right? Because you just have a force and a distance. So your work is just going to be force parallel, right, times the distance. And I actually want to show that, right, that the distance is right here, right? We'll call this our d equals 6 meters, okay? So then that's simply then going to be our 13 newtons times 6 meters, and 13 times 6 is 78 joules, okay? So the work done by the force, not just the parallel force, but the overall force is 78 joules, because the other part isn't doing anything, okay? So, okay, but then when might we need the mass, right? Like when would it matter? Like when would, it make a difference? Well, it might make a difference if we were, say, lifting it up. So what if our displacement was instead parallel, all right? So let's have it be, all right, so we'll have it, I don't want to give us too many angles, so I'll make it vertical, because you have to be careful about not introducing complicated trigonometry in here, all right? So I'll call this displacement, all right? It's going to be a new one, but we'll just give it the same letter. And we'll call this one 4 meters, okay? It points straight upwards, all right? And that means that we're going to have another force here, okay? And it's going to be a component, and I'm actually going to relabel them because we'll call this one the x component, and then this one we'll just go ahead and call it the vertical component, right? It's a little bit shorter, so it's about right to scale, okay? And so this is going to be Fy. The reason I changed the notation is because they're both parallel in their own right. So one is parallel to the 6 meter displacement, Fx that is. Fy is parallel to the 4 meter displacement, right? So we've kind of got naming conventions to match up with that versatility. This one, if it's going to be a component of the original diagonal force, realistically it should be something smaller. So looking at it, let's make it 9 newtons. Okay? So now we could ask a couple of questions. We could say then, if we lift it up that much, right? So if the force, so we'll call that A. So B, so if the force shown displaces the box vertically by 4 meters, then how much work does it do? Okay, and by it, it's the force, okay? Well, we still don't need the mass, but we'll get there, almost there, okay? Because now I'm just gonna say that the work done by the force, okay, is now force Y, and here to stick with my new notation, we'll call this one over here force X, okay? And this will be dx. That's really what I should have done in the first place. Make this dx over here, and then this one is dy. Right? So we just got two displacements. One's vertical, one's horizontal. Couldn't be simpler, right? Okay. And so in this case, this being the new displacement, the vertical one. So alternate case. Now it's Fy, because that's our new parallel force, times dy, and then that's just going to be 9 newtons times 4 meters. Okay. Which is 9 times 4, I guess that's 36, okay? So then that's going to be 36 joules, okay? So, why is that one smaller? Well, a couple of reasons, right? Because the force was smaller, right? Because I stuck with the idea that, that kind of angled force would have a smaller vertical component. And furthermore, the displacement was smaller, right? 4 instead of 6 meters. So it definitely makes sense that we should have less work done. Now, finally, though, how much work does gravity do? Okay, so, for this vertical displacement, okay, how much work is done by gravity? So hint, this is not an answer of 0, okay? I'm not looking for a 0. If we put this on a tabletop, at least in the first case where it's horizontally being displaced, maybe I could have asked for the normal force and expected a 0. But here, no. It's not going to be a 0, okay? Gravity is doing non-zero work here, okay? And we know exactly how much it is. And it doesn't matter whether the block accelerated or not, okay? In fact, maybe we'll go back to these numbers and see if it did, okay? Because that does not matter here. The amount of work done by gravity is independent of the work done by the vertical force, okay, Fy. All that matters is the displacement and the weight, okay? Because, right, so again, think if you can calculate it. I'm going to show you the answer now, okay? So if you want to calculate it on your own, do it now. Because the work done by gravity, okay, is going to be the force of gravity times the vertical displacement, okay, but negative. So I'll put a negative in front. Why a negative in front? Because the force and the displacement are not parallel, but rather anti-parallel. Still non-zero, but you get that negative tacked on, okay? Because if we were to look at the force of gravity, we know that the force of gravity points straight down, right? Probably not to scale here, but there would be the force of gravity, okay? Displacement is that upward pointing blue arrow, vertical displacement at least. Force of gravity as a vertical force by definition and points straight down. So then, right, we've got our negative because of the anti-parallel nature between the displacement and the force here, okay? And it would just be negative times the mass, finally using it, 12 kilograms, okay, times gravitational acceleration on Earth, because if you're not told otherwise, you better assume you're on Earth and better assume you're going to be using 9.8 meters per second squared, only round if you're told to, and then times the displacement of the vertical displacement of 4 meters, okay? So that's going to be the amount of negative work done by gravity. So let's go ahead and put that in. That's going to be negative 12 times 9.8 times 4, okay? So negative 470. So that's a big difference, right? So that means that in this case, we would actually have, to hint at something that we'll show in the next lecture, we would actually have a very large negative acceleration because gravity is doing way more work than the lifting force. So that means that we probably would have had to have it start already in motion. So, basically, otherwise we'd never get it moving in the first place. But if the block was moving upwards to begin with, but we had this little relatively piddly force of only 9 newtons, right, lifting it, that means we're not lifting it enough to actually keep it lifting. And that means it's slowing down and coming to rest, right? And it'll slow down and come to rest rather quickly, right? Depending on, this value of, much larger amount of work being done by gravity, okay? So gravity is opposing that motion and with a much greater amount, okay? All right, so we could do a power example, but I'll save that for later. The big thing that we'll see in the next lecture is tying this concept, quantifying work, and the simple definition of it just being parallel force times displacement, parallel as in parallel to that displacement, while tying that concept of work in with kinetic energy, which has that little, relationship 1/2 mv squared, all right? So that'll be the goal. That's what we'll do with this content. And I hope this introduction to energy and work and power has been both interesting and informative. Thank you so much for watching.